How do you prevent this from happening? You stick, yeah, sacrificial electrodes, right? These little, they're called that. It's not writing here. Yeah, zinc, good memory, right? Okay, you slap on some zinc. It'll react. Once it's all gone, then the chemistry will start attacking the iron. But this is also it. I put these in the water in 2011, and you can see the rusty nail and the nail that looks perfectly new. So which one's coated with zinc? Obviously, it's a brand new one, right? So if you're going to put up a fence, make sure you use what nails? There's the G, galvanized. Otherwise, you're going to be out there pounding it up in a couple of years. Okay, so a little bit of review. Oxidation states. The whole idea of this electrochemistry is bookkeeping. A lot of reactions in nature are electrochemical. And it looks odd how they happen, but in the backbone is just the transfer of electrons. That means something has to be giving up the electrons, the other reactant is just accepting them. And to keep track of that, we need some rules. We need bookkeeping. We need oxidation numbers. Here's the rules, right? And just to go over them, you have them in your notes, so, but everything, elements, iron solid, 0, right? Just elements sitting there all by themselves, okay? Oxygen gas, 0, right? Monatomic ion, it's just the charge, okay? Now so oxide, his oxidation state would be -2, he's just the charge. Oxidation number of hydrogen is always +1. Fluorine is always -1, right? Hydrogen's +1. We'll worry about the exceptions later. What are the odds of them throwing an exception in the homework? Compounds and ions. Sodium carbonate. How many oxygens do I have? 3. How many carbons? 1. How many sodiums? 2. All those atoms, add up all their oxidation states. I'm going to get what? 0, because it's the overall charge. If I have carbonate, add up the oxidation states of 3 oxygens and a carbon, I'm going to get -2. Right. Let's practice this a little bit here. KCl. Oh, we skipped the chlorine one. We said fluorine was -1. Here it is. Chlorine, bromine, and iodine, -1. So the oxidation number of chlorine must be -1. So potassium has to be +1. Okay. How about the nitrogen? Oh, we skipped. We didn't say that. Well, oxygen's -2 everywhere, right? So what would nitrogen have to be in nitrate? Now remember, you have 3 oxygens, though. I hear +3, +2. I don't know. Each oxygen's -2. So the total is -6. So this dude added up to a -6, get a -1. +5. Nitrogen has to be +5. Okay. Now the reason why we want to do that and be able to play around with it is so we can answer questions like these. All right. See who remembers this stuff. Cat. Oxidizing agents are always blank. What did you say? They're always... I kind of gave a hint, but not a very strong one at the beginning. You said electrochemistry. Something is giving up electrons. Something's reacting with them. Both those guys are reactants, so it's reactants. Okay. And always get, Amanda, you remember this? Reduced. Good deal. Oxidizing agents always get reduced. Kimberly, Oh, I don't know. Let's go back here. We said nitrogen is positive 5. Who knows what he goes to? Nitrogen and some blah blah thing. But if if this nitrogen is going to get reduced, what does that mean for his oxidation state, Kimberly? What could it be? If he's going to get reduced, what could be a possible number for him? Anything what? Anything above 5 or lower than 5? I can't change. It has to change, right? 5 is not. There's no change. Reduced means reduced. So reduced. It's a lot easier to think of it this way. You can think of it different ways. My brain just goes from A to B, the shortest and the least neurons required. So if it gets reduced, right? I'm saying this thing gets reduced. So if he gets reduced, his new oxidation state has to be less than 5. If this compound gets oxidized, well then his new oxidation state has to be above 5. So that's how I remember it. Okay. Let's answer the rest of this. This is probably, Jamesa, what you were thinking about. But let's ask Miranda. Miranda, reducing agents are always reactants and always get, keep going, always get oxidized. Yeah. Okay. Determine the oxidizing and reducing agents in the below reaction. So Adriana, what is the game plan to do this?
To figure out which elements or which of the compounds has been oxidized.
Yeah. Okay. So let's pick on one. Let's just pick on this sulfite. John, where would you start? Yeah. So each oxygen is what? -2. Maybe I should do color coordinated here. If I have -2, the full charge is -6. Now, that means S has to be, anyone see it? Has to be 4. I only have one S, so it has to be +4. All right? Okay. Who cares about the chromium? Just figure out what is on the product side. Is oxygen ever going to change on you? No. The sulfur will, though. So let's figure out what sulfur is on the product side, and we'll see whether the sulfur gets oxidized or reduced. And then we'll know what he is, and then the chromate just has to be the opposite. We don't need to mess with them. So let's do the sulfur on this side. So Pablo, what would you do first to figure out the sulfate? -2 times 4 is -8. So that means S must be, Adrian, +6. Okay. So this compound, he got your Randy, oxidized or reduced? He got, does everyone agree? Oxidized? Okay. He got oxidized, so he, Nyla, is the reducing. They're opposite. This is what kind of Jameis was talking about. They're opposite. Sulfite got oxidized, so he's the reducing agent. All right, now you can do the math. And if you don't believe me on faith, Casey, but chromate has to be the oxidizing agent, just the opposite one. That means that chromium had to have gotten reduced. Okay, if you don't believe me, you just have to prove it to yourself. It can be a you do. Charge, current, voltage, power. See if we remember this. Units. Erica, the question is about charge. What's the charge? Blah, blah, blah. What units are charge? You want to help her? Coulomb. C-O-U-L-O-M-B. Coulomb. How about current? Kathleen, current. Amps. Voltage. Jimmy, so you got an easy one. Volts. And power. Anna. What? 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 Watts. Right? Okay. Now we just want to use the unit because we never write out the whole thing, Pedro. What's the symbol? Oh, not the unit. I guess the unit, we should have this, right? Amp is what? No, it's not. We'll get to it. What is amp? What's the symbol? What they use? Capital A. Volt is, yeah, these are the units. I'm still on units. I didn't get off. A watt unit is, joules per second. That's down here. It's a big W, but it's watt, right? Okay, now the symbols. The Q, man, he remembers his physics class. Current. Little I or big I? Big I. Big V. Yeah. Nailed every single one of those. Yeah. Okay. So current is charge per unit time. Therefore, 1 amp is, not joule per second. That was watt. Current is, because a watt is a joule per second. All right, but that's not even, we don't even care. It's not even in here. But a watt is joule per second. Maybe that's down further. An amp, charge per unit time. So it must be what over what? Coulombs over seconds. Voltage, oh shoot. I forgot it. I'll be right back. Voltage is a field, and pretty much the only thing that you can imagine for a field, at least in my brain, that I can imagine, is hills and valleys, right? So, electrically speaking, energy-wise, a volt is energy per unit charge. So that means energy is joules, charge is coulomb. It's kind of a hill, an electrical hill. And I can get at the very top of the hill by generating a huge amount of voltage. And this is a Tesla coil. Okay. All right. So I can generate a lot of voltage. Okay? And if I get close enough, electricity always wants to get where? It always wants to get to the ground, disperse. Okay? So it's getting to the ground by jumping through here. It's actually ripping the air apart to get there. And that's that sound that you hear, the air slamming back together. Okay, that's what thunder is, right? The air slamming back together. But what I wanted to point out was that I can make this light up by putting it at the top of the electrical hill, getting it really close to this, right? Because the closer you are to here, the higher, if you want to think of a gravity analogy, right? You're really, really high. If you're farther away, you're off, okay? You see it light up? So it gets those little guys to accelerate and speed up and hit the sides and fluoresce. But that's the idea, okay, with electrical potential energy. Yeah. So voltage is just that, electrical potential energy per unit charge. A Faraday. 1 Faraday is the charge in coulombs of 1 mole of electrons. How many coulombs is that? 1 Faraday is, I could be wrong, but that's what my memory tells me. 96,485 coulombs. Well, we'll have to look at the, I give you this stuff. Just look at the top of the quiz if you need this. It'll tell you how many coulombs in a Faraday. It's just the charge in a mole of electrons. Typical relations. Voltage is what times what? Current times resistance. Power is current times voltage. Work is voltage times charge. Moving a charge in electric field. Okay. Some galvanic cells. The electrochemical cell to the right can be described by that chemical reaction. Okay. So we have zinc reacting with copper, giving copper +2 and zinc solid. So Jeff, so you have to kind of use your imagination here. You make the little connections and do it all right, and you can take a photo of it, and you get the little voltmeter to do something, right? Or you get the little light bulb there. Okay. After everything gets connected, the light bulb lights up. Is the system at equilibrium? Why or why not?
I would say yes, because there's power in there.
Does equilibrium change over time? Here's a hint. Does equilibrium change over time? All right. Is this an equilibrium? No, all right? So things shouldn't, concentrations especially, shouldn't be changing over time. That'd be equilibrium. Over time, is that light bulb going to get brighter, dimmer, or stay the same? All right? If it stays the same, someone just discovered endless power supply, which is completely impossible, right? It's going to get dimmer. Okay. So that's a hint. Is this at equilibrium when that light lights up? No. It's not. What you are doing is you're just somehow tapping into this reaction. Remember, electrochemistry is a transfer of what between reactants? Transfer of electrons. Bless you. And all they're doing is putting the reactants in different vessels. So to get those electrons to transfer, they're going to shoot it through a light bulb first. You're still going to end up reacting in the end. Okay, so it's definitely not at equilibrium. But as time progresses, what will happen to the light bulb? It will get dim. What will happen to the voltmeter in that photo? Yeah, that voltage is going to go down. Okay. When do you know equilibrium is reached, Kat? And the light bulb is dead. When the voltmeter reads, nothing, zero. It's done. Okay. So here's our overall reaction. Even though it looks kind of odd that you can separate compounds and have them react, but you can. It's just because electrochemistry is a transfer of electrons, so this works. Now, here's our reaction, even though they're in different vessels. What is the oxidizing agent? Amanda, what's the oxidizing agent in this reaction? Zinc, because it gets reduced. Yeah, right. Zinc is +2, it goes to 0. Zinc +2 gets reduced, so it's the oxidizing agent. Boom. Okay. Kimberly, recalling from past chemistry classes, assuming you had the tables, how did we get delta G for our reaction? I thought it was kind of easy. That's why it sticks in my head. What do we do to get delta G for a reaction? You had these tables. Anyone remember? You added up all the delta. You found a delta G first for every single compound in the reaction. Then you added up all the delta G's for the products, and then subtract out the delta G's added up for all the reactants. That's kind of like final minus initial. So that's how we did it a long time ago. Okay. Well, maybe not. Maybe skip that day. Okay. Delta G. This Gibbs free energy, it's called, is always blank for chemical processes, Miranda, that will definitely happen. They're natural. Delta G is always, what was the trend? It was always, Jamesa says negative. Yeah, it's negative. That's key to remember. If you added up all those delta G's for the product, subtract out the delta G's for the reactants, you get a negative number. Oh man, that reaction's going to go. It's going to happen. Otherwise it wouldn't. Okay. So that includes galvanic cells. You just hook this stuff up and automatically that light lights up. You can't stop it from happening. It's a natural thing. So that means delta G for that reaction has to be negative. Yeah, it's natural. Okay. So only for electrochemical reactions. We have a new way of getting delta G for a reaction here, John. Delta G is minus NFE cell. What is a numerical value for delta G for the galvanic cell described in the above photo and diagram? Ooh. Okay. What are we going to plug in for all this stuff? We want to get delta G. Well, the F part's not so bad. Yeah, it's that Faraday's constant, 96,485 coulombs. We know him. He said, just look it up, or top of the quiz, right? 96,485 coulombs. How about the Ecell? Kind of a trick question. You usually get this from a table, but I told you to look at the diagram. Look at the photo. You got to look really close. 1.08. And what units is that? 1.08 volts. Right. Oh, we should write down what F was. 96,485 coulombs. Okay. Well, you just read whatever the voltmeter reads, right? So Ecell, you just read whatever the voltmeter reads. Okay. In volts. How about the N? Pablo. They want to know what delta G is for this reaction. What's N? Moles of... Oh, you're so close. Starts with an E. Electrons. Moles of electrons. That's all it is. So all we have to do is look and see how many moles of electrons were transferred. Okay, do we have space to do this? No. Okay, let's figure it out then. The zinc goes to... Oh, sorry, zinc plus 2 goes to zinc, right? The copper solid goes to copper plus 2. I don't know if you remember balancing half reactions, but first you balance everything but oxygen and hydrogen. Well, there's nothing really to balance. So zinc goes to zinc. It's a charge. You have to add electrons to the most close, most positive side. Add electrons to the most positive side until the charges are the same. So if you're looking at that top one, here's the most positive side. How many electrons do I add to it? 2. Okay, we kind of already know our answer, but okay. And on the bottom one, add 2 electrons to the opposite side. So this is how it always works. And then you add things up. The electrons would end up canceling. If you had a 3 electrons and a 2 electrons, you have to do some multiplying to get stuff to cancel, right? But here the electrons are going to cancel just like they're written, 2 electrons. And we end up with our overall reaction if we added it up. It's a simple example, but it brings it out, brings it home. So what's my little n? Little n is the number of electrons that canceled. It'd just be 2. Yeah, my little n would be 2. Okay. So, Adrian, we don't need to do this. All I'm just saying is, would delta G be positive or negative if you did all the math? Negative. Did the light bulb light? Yeah. So it's natural. Delta G should be negative. Okay. It really comes down to Ecell being positive, because F can't be negative, N can't be negative. Ecell is the only thing that can screw you up. So positive Ecells are going to be natural. They're going to naturally happen. But you can have negative Ecells too. You have to force those to happen. If you want to get aluminum and recycle it, you have a huge negative Ecell to come over. That sucks up a lot of electricity. That's why it's the one metal that's worth money. You can recycle it. It's worth it because it costs so dang much to make in the first place. Okay. If a cell is galvanic, then its Ecell is positive. Galvanic means natural. It's going to happen. Okay. And here's some terminology. They say this, it all means the same thing. If they say, what is the cell potential, they could have just as well said, what is the cell voltage? They could have just as well said, what is the electromotive force? They could have said, what is the EMF? What is Ecell? All that is the same thing. And it's confusing. But all that stands for Ecell. What's the voltage of the cell? Ecell. What's the EMF? Ecell. See? So just kind of keep that all in mind. All that is Ecell. It gets confusing. Okay. Now, if you remember, I asked, what was Ecell? And someone said, oh, you use the tables. Okay. Well, yeah, if you can't read it off a voltmeter, you're going to have to use some tables. Okay, and it's going to be pretty rare for me to give you a picture of a voltmeter and have the voltage on there, right? But you could. But let's do it this way. Let's have tables. Well, if you're going to have tables, you're going to have to standardize everything. Well, Nyla, if you want to make that table and have all these voltages written there, all concentrations have to be what molar? Probably the most common, just the one. Just the one. And the pressure is, the temperature is, they don't pick, I don't know why. Maybe because it's too cold, right? You'd have to work in a refrigerator. 25. That's probably why, right? Okay. And so what they're saying is that one cell has to be, okay, whatever the heck you want to make it. But the other dude has to be an SHE. What does a SHE stand for? Oh yeah, something hydrogen. Standard hydrogen electrode. And if you want to know what it is, this is it down here. There's a picture of it. Okay. But so you have to build all these cells. You don't mess with the standard hydrogen electrode. Leave him alone. But the other cell, you just keep exchanging. And then you see what the voltmeter reads. And that's what all these numbers state. Okay? Okay. For all electrochemical reactions, we have that relation that we mentioned. How can this relation be rewritten for when the electrochemical reaction occurs under standard conditions? We want to write this equation again. You haven't seen this too much, I don't think. Whenever they say something is standard, they add little superscript whats? Zeros. They add little superscript zeros to stuff. Now, you only add superscript zeros to stuff that makes sense. You're not going to add a superscript 0 to the N. You're not going to add it to the F. But you will to delta G. You remember looking up those delta G's in tables? They weren't delta G's. It was delta G 0. Because you got it from a table. Everything had to be standardized. Ecell has to be a 0. So not much really changed. Just saying, hey, we're at standard conditions. You can use tables. That delta G 0, you can use this equation to get it. You don't have to. You could add up all the delta G products minus delta G reactants and get it that way too, if you had the table. Okay, the same standard conditions. Kind of nice that way. How is a table of standard reductive potentials used to describe or used to find E0 cell? Ouch. Okay. Any ideas? I think this is how you do it. Right? You just look up the half reactions and you have to add them up. Right? So you find the two half reactions. Now, one thing that's kind of odd is the electrons are always what? On what side here? They're always on the reactant side. So you can't take two of these and add them up as is. One of them you have to flip. Okay, so fine. So you pick two of these guys. Just pick the bottom two. I don't care. Pick the bottom two. You want to make a reaction out of this. This isn't, if you just add them up like this, first off, the electrons aren't even going to cancel. Doesn't make chemical sense. One of them has to be flipped. Fine, you flip one of them. Right? Now we kind of picked a bad example here because they're going to both cancel on us easy. Those two, we don't have to multiply through by nothing or anything. Let's pick some that you do. Let's pick the nickel. And here's one. It only has one electron in it. Okay. And let's say we want to flip the top one. You have to flip one of these. If you flip the top one, what do you do to its E0 value? You have to make it a negative. Right. So if you flip a reaction, you make it a negative. See if you remember this. Here's the real kicker. Now to make these add up, you have to, what do you have to do to that iron reaction? Multiply it through by 2, otherwise it won't cancel. Good, you're following this perfect. Okay, you multiply that top reaction through by 2. First you have to flip it, right? And you change that sign. I can't even see what it is. What is it? It's this one, I think. So you have a negative 0.77 sitting there. You multiply through by 2. Do you have to multiply that negative 0.77 times 2? It's a potential. It doesn't matter how much of that stuff you have. It's the same. So you can multiply that reaction through by 3, 4, 10, divided by 6. It doesn't matter. You never change that number. All you can do is make it plus or minus. It's the only thing you can do with potentials. So you need to remember that. That's kind of a key point. Okay. Oh, here's a good example. Find delta G0 for the unbalanced overall galvanic cell reaction. Okay, so let's write our equation here first so we know what we're doing. Okay, so we got to figure out what E0 cell is. We got to figure out what N is and all this stuff. So, where's one of my half reactions? I need copper and I need nickel. Copper plus 2. Here's copper plus 2. Okay. Do I write him as written there? Or am I going to flip him? Is there another one? Oh, here's another one. Oh, good question. Which one do I want to pick? I'm going to... Oh, yeah. Thank you very much, Nyla. I might have wrote down the wrong one. Make sure you go to the one that has a solid in it. Which one is that? Oh, thank you, thank you, thank you. Too bad I'm not tossing out candy bars. Yeah, we're getting... Good point. You see that? We got to pick that top one. Do I want to flip it or leave it alone? Leave it alone, because otherwise it's going to really mess up that copper solid. So it's copper plus 2 plus 2 E minuses. Copper plus 2 plus 2 E minuses goes to copper solid. I'm going to write down that E0 number right away. It is 0.34 volts. Now I need the nickel, and the nickel plus 2. All right, isn't that one right there? Now I have to flip it though. So nickel solid goes to nickel plus 2 E minuses. And now I had to flip that guy, so I need to write down what volts? Positive 0.25. Okay. If you need to multiply through by stuff to get the electrons to cancel, you do it. Just don't mess with the E zeros, right?
Oh, okay.
Don't mess with those. Once you did your sign flipping, don't mess with them, okay? But they're going to cancel, so we don't need to multiply through by anything. And then we end up with the exact same reaction we have. So that works.
So, Dr.
All right.
Just so I can,
Mhm.
if I understood this right. So if you have a reaction in which the electrons don't match, you have to multiply it by a number.
Yeah,
in
let's
order to make
let's mess with it. Let's pretend this dude was a 3.
But the Ecell doesn't change at all.
No, but let's pretend. Let's pretend he's a 3. Then you have to multiply the bottom one by 2, top one by 3, but don't mess with these voltages, right? Okay. Now I need that E0 cell number though. That's going to be 0.59.
Were we supposed to balance this? It says question
Why is that unbalanced?
It's balanced, isn't it? Because I made it up and I'm just trying to make up questions. I need to pick a better one. I need to pick a better example that has like a 3 and a 2 in there or something, right? But whatever. Okay. So if you add up those voltages, you get 0.59, right? So my E0 cell is 0.59 volts. My F is 96,485. And my N, everybody, is going to be 2. So I can get my delta G0. Okay. What would be the units of my answer? What would be the units of my answer? Volts is joules per coulomb. F is coulombs. Coulombs cancel. Joules. Because delta G is energy. So I'll get joules. Okay. Let's see if we can answer some questions like this number 2. A stronger oxidizing agent. Iodine solid or tin plus 2. Now oxidizing agents get reduced. Now before we even look at that table, oxidizing agents get reduced. Before we even look at that table, should this I2 and this SN plus 2, where should they be on that table? Should they be reactants or should they be products? They should be reactants. If you caught that, that's really good because I didn't even mention it. The table is called standard reduction potentials. So they're always written as reduction potentials. So we want to look over here and find, what were the two? I2 solid and tin plus 2. Thank you. Where are they?
Below it.
Yeah, because it has to be getting, because you notice what Kimberly said. Here's tin plus 2, but that tin plus 2 is getting oxidized. So no, we're talking about things getting reduced. Because the question is oxidizing agents. They get reduced, right? So one thing leads to another. So they get reduced. So we got to look for stuff that's getting reduced. So tin plus 2 is getting reduced here. The other one is I2 solid, way up on top. It's getting reduced. A lot of chemistry here. They're saying which one is a stronger oxidizing agent. Which one of these reactions, which one of these half reactions really wants to go as written? Imagine doing this game. You write the reaction, you add up the potentials, right? You want a really big positive number for your cell voltage. Look at the equation. You want a really big positive E0 cell for it to be spontaneous. to be a really big negative number because you multiply by a negative. So the more positive, the more likely it's going to happen. Which one is a stronger oxidizing agent, I2 solid or tin plus 2? I2 solid. Just imagine putting that number in there, a positive 0.59. Comparison to, man, this one doesn't even want to be an oxidizing agent, right? It's negative. He's going to make things less spontaneous. So I2 solid is the answer.
It's based on perspective chart, right?
Yeah, it's because you're playing this game, adding up reactions. The strongest okay, you really follow what I'm talking about if you can answer this question. The strongest reducing agent in the table is, take a look at the table, identify what a reducing agent is in the first place, take a look at the table, see what you think. Okay. Casey, what did you say as an answer? What compound? What chemical? CO2 plus? She says CO2 plus. I hear mercury. Okay. Let's start at the beginning. Strongest reducing agent. That means it has to get oxidized. So if you're going to guess something, you better guess something that's written as a reactant or a product in this table. Has to be a product. Okay, has to be a product. So if you're looking at a product, so now they never do this. They should have a table of standard oxidation potentials, right? It would be this exact table. Everything would be, all the reactions would be flipped. And then you do what to all these signs? Flip them. But they never do it because they expect you to do that. So if you're looking at oxidation, you're supposed to imagine, okay, I got to flip all these reactions, and I got to flip all these signs. So now your answer would be what? You want the most positive. It would be the CO what? CO solid. Right? Because you have to flip all these guys. So notice how it can't be CO plus 2, because CO plus 2 is getting reduced. It has to be something that's getting oxidized. Right? Because the very question was, what's the strongest reducing agent? Then you got to do that trick. Okay, if it's a reducing agent, it has to get oxidized. So you look for something that's getting oxidized. Not only is it getting oxidized, but it's going to get oxidized with the highest and most positive E0. That's the trick. Okay. Maximum work. What are the units for work? Miriam, what were the units for work? Joules. Good deal. Okay. If Wmax is the maximum work that can be obtained from a Wmax is the maximum work that can be obtained from a galvanic cell, what is N? Yeah, good question. This is what tells you when a battery dies. You want this little AAA battery to kick out so many moles of electrons and the damn thing's dead, right? That's all it is. N is the number of moles of electrons that were transferred. And if it's not that well built of a battery, well then your little N isn't going to be as good either, right? So N is just the number of moles of electrons. So let's see if we can make sense out of that with a question like this. It's the number of moles of electrons that were I mean, you can keep talking about this, that were transferred between the oxidizing agent and reducing it, right? But just say were transferred between reactants or something, right? For this reaction, what is the maximum work that can be performed? If 63.5 grams of copper solid is formed. Okay, maximum work. Miriam said the units of your answer have to be in joules. Okay. We're going to have to use this equation. Okay. So, Ecell, the questions, I just wrote this too. Ecell should be, they have to tell you what Ecell is. Let's say the cell voltage is, did we get a standard value for that? Yeah, we got 0.59 volts. Let's just say Ecell is the standard, which is 0.59 volts. They have to give it to you. Otherwise, you can't plug in a number for this guy, right? Okay, so we know him. F is what number? 96,485. We just got to get the moles of electrons. So we're going to convert what to moles of electrons? The 60 point. We're going to convert the 63.5 grams of copper. It's just one compound to another. That means we need a mole bridge. Need a reaction. 63.5 grams of copper. Well, let's go back into the inner workings of this thing. If you use the overall reaction, that's where it seems problematic to me. Let's go back here. If you use the overall reaction, I don't see electrons in there anywhere. Well, you can't use that reaction. I don't see a mole bridge with electrons in there at all. So what you could do is find the half reaction that has Cu solid in it. Right? So you can just go to the table and find it and see what the mole bridge is from that table. Right? But you might be kind of taking a chance there, because I kind of almost screwed up where Nyla pointed me out. There might be copper solid in more than one half reaction. So you want to make sure you pick the right one. So you might want to write the half reactions for this overall reaction. And that'll tell you exactly which half reaction you want. You want the one of copper plus 2 going to copper solid. That's the half reaction that we're interested in. Without even looking it up, you can probably tell what the number of electrons is. 2, right? It's 2. So for every 1 mole of copper solid, we have 2 moles of electrons. If you had to balance this thing and multiply through by a number, it doesn't matter. It's the same ratio. If you multiply through by 3, you'd have 3 for 6. It still doesn't matter. It's the same ratio. Okay. So we need 2. Oh, no, we don't. That's our mole bridge, right? When we need it, we'll have it. We have 2 moles of electrons for every 1 mole of copper solid. So it looks like we just need to do what first then? Convert the grams into moles. Yeah. Convert those grams into moles. What is it? 63.5. Thank you. 63.5. Ah! I did. Shoot, I got to make these more difficult. 63 grams of copper and 1 mole copper. So the answer is just 2. Huh? I bet the handout's not going to be that easy, right? But that's the idea. You just grab the reactant, its amount, use the half reaction that'll give you the mole bridge between whatever that reactant is, or product, doesn't matter, and the number of electrons. And you can get the number of moles of electrons transferred to get maximum work. We made it. Okay, so I believe you have everything you need to knock this out. So come by if you have some questions.